happens is that we need to learn why do we need to deal with with design at all. What is the reason to deal with design? Why deal with design? Design acts as a bridge between requirements and code, and it splits a big system into a smaller one, into manageable pieces so you can support the right tasks and control costs and quality long term. Meaning, if you need to update the screen design, you only touch the screen box, the brain box stays perfectly untouched. So you design into manageable pieces, different manageable pieces, okay? And in that way, you split the big scary system. You split the big scary system up, right? For example, you put it in different layers, and you control quality. And the hardware box, the brain box, catches it safely, displays an error message on the screen, and safely splits the user card back out. Controls long-term cost, makes changes cheap and easy. If the bank decides to add a new task like withdraw a QR code, developers just plug a QR module into existing design rather than rewriting the whole ATM from scratch. Now what happens is that a domain data model. In domain data model, what we understand is that we have a customer, we have a bank account, we have a let's look at things, the classes. And we know that the classes are, for example, customer, bank, account, debit card, and ATM transaction. These are real world objects or concepts in business. The attributes are, for example, a bank account has account number, has a balance, has a card number, and has a PIN. Has attribute. It's an attribute. Has relationship, has a. These are attributes. Classes are real world thing. Customer, a bank, of course, a bank also has customers and has a bank account and has a debit card, but these are real world objects in business. It's just basic information belonging to each thing. For example, to each bank, a bank account has an account number and a balance and a debit card. These are attributes. A bank account, for example, just like I said, and relationships are how these things connect to interact with each other. For example, a customer owns a bank account. An ATM transaction withdraws money from a bank account, and things like that. So why it matters is that if your domain model is wrong, you will code the wrong system. For example, if your diagram doesn't show that one bank account can have multiple debit cards, for example, for a husband and wife, the programmers will build a system where only one person can ever have a card, ruining the entire bank's business requirement. It's about business requirements. Now we need to understand that where does the domain data sit among all level of abstractions. So in the context, the broad experiment and business goals, this is what happens here. And why? Because the bank needs to reduce branch lines by offering 24/7 self-service cash machines. Domain data, the real world business concepts, rules, and data entities. For example, defining what a bank account, account balance, and PIN mean to the bank before you even think about screens or code. Interaction, so how users directly talk to the system, how the customer inserts a card, types their PIN on the keypad, and selects an amount. System, the actual inner software code and database tables. This means that the code and internal SQL database running update accounts, etc. And why it sits on level 2, the domain data sits on top because it describes the client real world business realities, not the computer software. A bank account and a account balance exists on paper ledgers long before computers were even invented. You must define this real world data at the domain level first, so you know exactly what your interaction screens and system code are actually processing later. And now, how do you identify domain data from descriptions? You need to understand that you find domain data by analyzing your written text requirements like user stories or descriptions using a simple 3-step linguistic filter. So imagine a client gives you this raw description that our user inserts a debit card into the machine. The customer then enters a secret code to check their checking account balance. And here's how you clean it up to find the actual data entries. So step one, find the nouns, okay? Highlight every single noun, person, place, or thing in the text. And after that, you extract users, debit card, customer, code, account balance. So you know person, place, thing. Person, place, and thing. These are nouns. So you extract them. You extract users, you extract debit card, customer, code, account balance. These are nouns. Then you remove synonyms, delete duplicate words that has the exact same thing in the business. For you realize users and customers are the same person. You keep customer and delete the users to avoid developer confusion. You clear up vague terms like replace fuzzy words with precise business vocabulary. Secret code is too vague. You rename it to the PIN. Account balance is a detail. So you connect it to main entity bank account. Just like I said, secret code is too vague. You rename it as a PIN. You don't keep it. You clean domain data list becomes customer. Your clean domain data list becomes then customer, debit card, and bank account. These are the exact boxes you will now draw in your final UML class diagram. Now, what is an association and how is it read and annotated? An association is a line that shows objects. For example, it's a line between two classes in a domain model. It shows that objects of those classes are connected in the real world. It is annotated with a name, a reading direction triangle, and cardinalities, for example. Now, imagine connecting a customer class to debit card class. You cannot just draw a blank line, right? You must annotate it so anyone can read the business rules instantly. Association line, a solid straight line connecting two boxes. So connects the customer box to the debit card. Customer connected with debit card. These are two boxes. You can connect them together. And then the name and the triangle holds. So for example, like this. Specifies the relationship and how to read it. Customer holds debit card. The arrow prevents reading it backwards. So you know that customer holds debit card. It's not the other way around. Then you know that this holds this. So customers holds debit card. This prevents reading it backwards as debit card holds customer. Left cardinality at customer 1. A physical debit card belongs to exactly one customer. So right cardinality at the card. So 0 to many here, just like that. That a customer can hold 0 cards, new account, or many cards, multiple checking cards. And always read from one class across the line to the other. For example, one customer can hold 0 to many debit cards. One customer can hold 0 to many debit cards. One debit card is held by exactly one customer. One debit card is held by exactly one customer. So one debit card is held by exactly one customer. And this is very clear, okay? That one debit card is held by exactly one customer. Now we need to look at the 4 UML navigability cases. We know that which object knows about the other project. Navigatability tells the developers that which object knows about the other object and how the data can flow between them in code. For example, unspecified, not yet defined. This is a case, right? It's a plain solid line, no arrows. The connection exists, but we haven't decided the data flow yet. Customer line, customer with bank account. So they are linked, but we haven't assigned who calls whom yet. Bidirectional, two-way. Plain line or arrows on both ends. So like this. The customer object has a list of their cards and the card object knows exactly who its owner is. Both object knows about each other. You can navigate the code both ways. And this way we understand that the customer object has a It has a list of their cards, and the cards object knows exactly who its owner is. Then we have unidirectional, which is one way. Unidirectional is just like this. Know this, only one side. Meaning that only starting object knows about the target has no idea the sender exists. So we can give a new example, like ATM goes to core bank server, and the ATM software calls the central server API to verify a PIN, but the central server doesn't store permanent memory of individual ATMs. So in that way, it's one-sided. Then we have restricted, strictly blocked. So line with the X on one end with this. So we can say that navigatability is explicitly forbidden in one direction to protect security or performance. For example, receipt printer comes here and goes X here, cannot go to customer account. The account system can send text to the printer module, but the receipt printer software is strictly blocked from reading or accessing customer account details. So he cannot read the details there. He can of course receive it, but he cannot read the details of customer. That's why we have a cross. And if we try to look at the next, that what cardinality is written in UML, we will understand that exactly one. So for example, one bank account, a physical debit card must be linked exactly one specific bank account. It cannot float around unlinked or belong to two accounts simultaneously. So it cannot be linked to two accounts. One bank account is linked to only one. Many or zero to many. Zero or many. A bank account can, so for example, ATM transactions. A bank account can sit idle with zero transactions at all, or it can have hundreds of cash withdrawals over its lifetime. So a bank account can just have no transactions, or it can have hundreds of transactions happening all over the time, right? Then we have one-to-many relationship. One to many. And in one-to-many, we might say an ATM vault must contain at least one physical money bill tray to function, but it can hold several to split different denominations like 10, 20, 50. But it must at least one physical money bill tray to function. This is cache castets, so one to many. Then we have specific range, min max. Digit PIN, for example, 4 to 6. The bank security system restricts the security code format. A valid user PIN must be at least 4 or at max 6 digits long. Then we might even understand that what is aggregation here, for example, and what are the two properties that it does have. So we need to understand that aggregation is a relationship in UML diagram showing a has-a or part of connection between parent class and a child class, the part. So it is drawn as a line with a hollow diamond pointing at the parent container. So aggregation is bounded by two strict properties, for example, transitivity and anti-symmetry. If C is part of B and B is part of A, then C is automatically part of A. So if C is part of B, and B is part of A, then C is automatically part of A. And this is obvious, right? So because this is a big box, it already has B and C in it. So if a physical money bill dispenser is part of a cash wallet, then the cash wallet is part of ATM machine, and the money bill dispenser is structurally part of the ATM machine. And anti-symmetry is if B is part of A, then A cannot simultaneously be part of B. There is a strict hierarchy. So if B is part of A, then A cannot simultaneously be part of B. So it cannot exist. So of course A is in B, B is not in A. Like, this is not a B that is inside of it. So A contains B, B doesn't contain A. So if a card reader is part of an ATM machine, it is physically impossible for the entire ATM machine to be stuffed inside that tiny card reader. That's what we understand. And weak versus strong aggregation. We can understand that a weak aggregation or a strong aggregation comes down to life cycle and ownership. Can individual parts survive if the main container is destroyed, for example? And the UML notation is a hollow diamond like this, filled and solid diamond, independent. So weak aggregation is independent. The parts can survive on its own if the whole is destroyed. That's a weak aggregation. A strong aggregation is composition dependent. These parts are completely destroyed if the whole is deleted. Multiplicity. The part can belong to multiple parents over time. That's a weak aggregation. And a strong aggregation, the part belongs to exactly one parent at a time. Concrete ATM example, for example. ATM, for example, security guard. ATM is a weak aggregation to security guard. And for weak, this is a weak relationship because ATM can independently exist. If the bank closes and demolishes the physical ATM, the security guard doesn't cease to exist. They just walk away and go back home at a different branch. But for ATM and screen monitor, if there is no ATM, if you smash the physical ATM with a sledgehammer, the built-in screen monitor inside it is completely destroyed and discarded along with it. So it is a weak aggregation. It's a strong aggregation. So with weak aggregation, the diamond is like this. It's a weak, but with strong, it's filled. It's a filled diamond. Now we need to understand the three key questions to decide strong versus weak aggregation. Question number 1, encapsulation. Is part hidden and only visible to the whole? That's the first thing. Second thing, encapsulation. If the answer is yes, then it's strong. The internal vault mechanism is completely invisible to the outside world. Only ATM software knows it exists and can control it. Second is life cycle. Does deleting the whole automatically destroys the part? Strong. The part cannot exist in code or reality without its parent container. Yes. If you delete the ATM object from the database, its local screen interface dies with it instantly, meaning it's a strong. Propagation. If yes, does copying the whole automatically copy the part too? That's the third thing. Propagation. If yes, does copying the whole automatically? Yes. Making a duplicate of the parent requires duplicating inner childs as well. So if bank orders exact duplicate copy of ATM model, the new machine also comes with its own cash dispenser unit inside of it. So if the answers to this question is no, meaning the part is shared and can survive on its own, existing independently, and you can use weak aggregation in that case.